Davis Rochesky, we have him.
Okay. Dr. Camarda.
Hey, how you doing, Richard?
All right, really good. Thank you for doing this. All right. This is our team this year. Also, there may be some teachers coming in. I was able to recruit a couple of teachers. You inspired me with your conversation yesterday. So I have a history teacher who wants to get involved in the project, and I have 2 business teachers that'll help these kids draw up a business plan so that their program, their proposed solution is financially sustainable.
Oh, wow. So we have some business students, potential business students, entrepreneurs in the class?
Yep.
Yeah?
Absolutely.
Let me see a show of hands there. Who's going into business and wants to be an innovator? All right. All right.
This gentleman here has started his own company. He's working on a patented design for a firefighting vehicle.
Excellent. Excellent. You're just the person we need. We need lots of different people to accomplish what we want to do, guys. And you want to know something? You're the ones that are going to make it happen, because I'm going to be like too old to do this stuff in a short period of time, and it's going to be your generation that's going to make it possible. Okay, we are going to have people living, working, exploring other planets in your lifetime, and we're going to make this happen. And it's not going to be just this country alone. It's going to be every country almost around the world, and we're going to do it together. It's going to be a collaborative effort, much like how we developed the space station. The United States tried to go it alone, but it was very difficult. It was also very expensive. We partnered with Russia. Ends up we have over 15, 16 countries that helped us actually build the space station. When you think about that, it's pretty remarkable. So, do we have questions for the class? Any questions?
Well, they seem to have questions about, like, what's involved in the project. So
Okay.
if you could introduce them to the different choices that they have, different parts of the project, and I'm sure they'll have detailed questions after that.
Okay, the project is really what I call an epic challenge. Okay, and what that means is we're going to be looking at a problem that's very difficult, almost impossible to solve, or it's very difficult to solve. It's very complex. And so if you can imagine going to the moon in my lifetime was an epic challenge. It was something that, wow, we had, the technology was almost there, not quite, but it was a tremendous challenge for this country to undertake as a single nation. So now the whole journey of exploring Mars, you can imagine all the different technical, social, environmental, psychological challenges that we have to overcome, okay? And every one of those is very important. How do we maintain and keep humans healthy so that when they land on the planet, they're able to function after being weightless during the transportation phase of the flight, which could last 3 to 6 months, depending on whether you have chemical rocket propulsion, whether you have nuclear propulsion, ion propulsion. And so these are the different, this is what we call, in design terminology, an ill-conditioned problem. It's open-ended. There's not one solution to this problem. There are millions and millions of solutions to this problem. And every one of those solutions has advantages and disadvantages. And so we have to look at the entire picture and then try to identify which attributes of the design are important, because for every design feature, it might have a positive effect on one system and a negative effect on another system. Okay, if you can imagine, protecting the astronauts is very important from space radiation. Something we never had to worry about before, other than the astronauts that flew to the moon. All of the astronauts have been in low Earth orbit. okay, about approximately 200 miles off the surface of the Earth. Not that far off the surface of the Earth when you think about it. And so they were protected by the magnetic field of the Earth. And now we're asking these astronauts to travel 3 to 6 months in deep space where we're not protected, and cosmic radiation can seriously affect the health of the astronauts. Okay? So, for students that are interested in medical, biomedical, how do you protect the astronauts from these effects of cosmic rays? If you're interested in materials and structures, how do you shield the astronauts from these cosmic rays? If you're into physics and electromagnetics, is there a way to basically develop an active magnetic field around the craft as you're flying? And so there's lots of different solutions to these problems. If you're interested in psychology, sociology, how do you select the right crew to take this journey? And once you get to the planet after 6 months, you have to stay there for over a year in order to be able to travel back in a timely fashion. Basically, the planets align, the orbits are such that you could blast off from the surface of Mars and make it back to Earth in a timely fashion. And so, how do astronauts have to survive in close quarters for extended periods of time? Socially, what are the attributes and the social dynamics of each one of the team members to make sure that they work together constructively and optimally as a crew for that length of time? And so, whatever your interests are right now, you can apply that to this particular problem. Let's, I tell you what, Richard, let's talk about what are the passions of the different students in the class, and see how it pans out, how it applies to this particular problem.
Yeah. Well, let's start here with Hunter, and we'll just go around the room.
What do you like to do, Hunter? What would you like to do?
I like to build things both theoretically and physically. Just in terms, pretty much anything. I'm working currently on like the landing gear of the Orion space capsule.
Excellent, excellent. And you know, one of the epic challenges we solved was solved by a crew of a team of young one graduate student and 8 undergraduate students designed a system that would protect the crew if the capsule landed on land. Okay? And what I'm going to do is, Professor Lachewski has that report, and he can show you what these students were able to do. And what I'm telling you is that NASA has not been able to solve that problem, and the team of students solved that problem. So if you like to build things, can you think of a few things we might need to build in order to fly to Mars and land on Mars, and maybe when we get to Mars?
Yeah, Dr. Camarda, the device that Hunter's holding, this week we're going to be dropping that off the roof. It's his version of the Orion system for protecting the astronauts, and he's got 2 eggs inside, which successfully survived, what, 15 feet?
Yeah, 15 feet drop onto tile. So far.
Hey, Richard, were you involved? No, you weren't in that team that we did that, but that's basically what we used as an icebreaker. Mm-hmm. When we met with about 30 NASA engineers, young engineers, and I wanted to teach them how to think outside the box to come up with some innovative challenges, and we had exactly that. We had 2 eggs, and we were looking at mechanisms to protect those eggs, and those eggs are the 2 crew members, right, in a space capsule. And so this is really cool. You'll really like following what these one MIT student and 8 students, undergraduate students from MIT and Penn State did, okay? And what you can also do is tap into the lectures by some of the experts that were looking at the landing dynamics, okay? When you study, and when you continue to study in high school and then go, let's say, to become an engineer, what you're going to learn are structural mechanics, impact dynamics, the dynamics and how they affect the structure, how the structure crushes to absorb the energy. And this is like stuff that you could start learning right now, as a matter of fact, by going online. And so what I want you to do when you think about, building things and testing things that we're going to need to go to Mars, there are millions of things we have to build. Now think about what's different about Mars, okay, is that we don't want to have to lug this stuff to Mars because it's very expensive to lift it up, that weight, off the gravitational well of the Earth and get it into space. So wouldn't it be great for us to use the material on the surface of Mars to actually build stuff on Mars using robots? Why not let robots do what they do best? To put a human being on the surface of Mars and keep them pink and healthy, right, takes a lot of work. You gotta put them in a spacesuit, you gotta make sure, and it's dangerous. Why not use robots for what robots are really good for? And so Professor Wachowski is very expert knowledge in chemistry. You could start evaluating what are the types of materials on the surface of Mars, and how can you use those materials and actually build structures and vehicles and habitats on the surface of Mars. Okay, let's pick another interest, another student that has an interest, and let's go through this.
Charlie, if I can interrupt for a second. Miss Massey just walked in. She's one of the English teachers that is going to help us with the project.
Hi.
All right.
Hi, Miss Massey.
How are you?
Hey,
It's
you know,
Dr.
this
Camarda.
is what we're trying to do, Miss Massey, is show how every single subject that these students are learning in high school, how important it is for us to be able to do these tremendous challenges. Okay, and so English, communicating, being able to communicate what you're experiencing, and being able to write about it. Not only technical writing, okay, but also writing to inspire other people, to be creative, okay. Writing is very creative, okay, and you can use that as a tool to inspire people to see what you're seeing as an astronaut when you're in space, to describe the environment, to get other people to think of other ideas to solve the problem, okay? And so being able to communicate correctly in the written word, both technically and both as an artist, if you will, to get people to be inspired and be motivated is a very critical skill. It's also very important for the young gentleman in the front that's going to be an entrepreneur to be able to sell your ideas, okay? What language do you use to the audience that you're speaking to in order for you to sell your ideas? First, to make sure that the people understand your idea, and then be able to sell it to them in very simple terms, okay? What's very critical in communication, we lost 2 shuttle crews because engineers were not able to communicate the problem successfully to upper management. Upper management did not understand the problem, and so they made the wrong decisions. So communication is very important, okay? So pay attention in English class, okay? Just because you want to be a scientist or engineer doesn't mean you don't have to be a good writer, okay?
Thanks for the plug.
Is that a good plug, Miss Massey?
Absolutely.
All right. Any other passions that we have? I guarantee you that for every student in this class, how many students do we have? 2, 4, 6, 8, 10?
12 in this class.
Okay, I'm missing a couple. I can't see them all. But anyway, for every student
we're
in
two
this
out.
class,
Not here.
for every student in this class, I guarantee you, if you have an interest, if you have a passion, it can be applied to helping this team solve this problem. And it's very critical to solving this problem. Even though the problem may seem totally technical and you might not be interested, you might be interested in math, You might not be as interested in science. What your interest is going to be very critical to how we solve this problem. And it's gonna be a team effort. Go ahead, Rich.
Yeah, no, I say James is interested in programming. He programmed his own video game from scratch.
So you understand how programming can be used for this problem, James?
I guess a little bit, yeah.
You understand why we need programming for this problem? Yeah. I mean, everything we're gonna run on this spaceship, when we land, in our homes, is run using computer programs. How we communicate requires computer programming. Now when you think about what makes this problem interesting going to Mars, right? How fast do electrons move, James?
Very.
The
I don't know exactly.
the speed of,
Oh, like.
right? And so how long will it take an electron to go from Earth to Mars? Depending on what the orbit is, it could be 20 to 40 minutes, okay? So what you're talking about is a time delay of 20 to 40 minutes, all right? So when you think about communications, or when you think about how do you design a robot, and we have robots on the surface of Mars, how do we design the software that automatically controls what that robot does without that robot falling off a cliff or getting stuck into very fine powdery regolith on the surface of Mars, which one did, by the way. Okay, so you have this time delay. And so what you need to think about when you're designing robots, okay, is designing them to be autonomous, to need as little help or communication with the ground as possible, okay? And the folks that do that best are the people at the Jet Propulsion Lab. Totally different type of programming. The other thing you might want to think about for programming is, how do you create an environment to entertain the astronauts, to teach and train the astronauts as they're flying in space, using virtual reality, using computer graphics, okay? We need to be able to train astronauts much more effectively. When I trained to fly in space, we basically went in simulators, and the programming that was necessary for us to operate the robotic manipulators that we used in space had to be totally accurate, so that when we tested on the ground in those simulated environments, like a video game, the way that arm operated physically in space in zero gravity was exactly how we trained, okay? And so computer programming is totally on every piece of equipment we're going to be flying and in everything we do. It's according to what your interests are. If you're interested in robotics, there are going to be lots of robotic systems.
We have Megan and Carla both worked. See, everybody here, we, as a warm-up exercise, we let them invent something of their own choice and then build it and test it to their specs. And Carla here and Megan worked on devices to keep beverage warm enough, like for baby bottles or for coffee. And that has a lot of applications in space.
Absolutely. I drank a lot of coffee in space. And so the skills you're learning, for instance, when you're doing that, is all about thermodynamics, heat transfer, probably electronics, and how you heat systems like that. So, Rich, you said they did this. Was this something that they did during your first semester, or
Yeah.
the first part of the first semester?
Yeah, that's what they did during the first semester. We let them pick their own design, subject to my approval, and then they designed it, they put it on paper, then they actually built it, and then they tested it. But they made up a criteria for their grade, like if the bottle would keep warm for so long, or if the Orion space capsule could be dropped from so many feet. 2 students built bridges, and they had to withstand a certain weight. And then they wrote a report on it, which is online, and they're doing oral presentations this week. So they're getting used to speaking and getting their ideas out there.
Excellent, excellent. The other thing we wanna teach them, and you're working in groups, in small groups, working in teams, right? Because
Right.
everything we do, especially when these problems are so complicated, we have to work in teams. We have to get along, and having a team that's very diverse is very important. I see you got a pretty diverse class, right? You got
Yep.
kids from lots of different backgrounds, lots of maybe different ethnic backgrounds, religious backgrounds, geographic locations, different cultures. This is very, very important. Okay? It's not just important because it's politically correct. It's important because if you want to be creative, if you want to be innovative, you have to listen to people that have different ideas. And you have to listen, and you have to pay attention to when other members of your team speak. Because when they look at the problem, they're looking at it with different eyes. They're looking at it through a different lens, okay, and with different experiences. And then they have to be able to articulate what they're seeing to you. And you have to pay attention, because it makes you think differently, okay? You have Russians that have flown in space, you have Americans that have flown in space, and now we have Chinese that have launched people into space. When you look at the way these people solve very similar problems, they came up with different types of spacecraft. They came up with different types of spacesuits, okay? Why? What principles did they use in their design processes that made them come up with different ideas? Take a look at those different ideas and understand those ideas, because then you can take those ideas and maybe help to design a better spacecraft for your country, okay?
Yeah, next week they'll be taking the cognitive mode survey and then dividing ourselves up into possibly 2 teams here.
Excellent, excellent.
Charlie, you think there might be an opportunity for the students to present, or even to watch the university students present in May?
Absolutely, absolutely. Now, the teams that we're working with right now are teams from Finland, which is going to be really cool. Oh, as a matter of fact, Tim Kopra, the Finnish astronaut, actually he's American, but maybe his grandparents came from Finland, is going to be launching from Kazakhstan in Russia in about an hour, I believe.
Cool.
1700 Kazakhstan time. I forget what that equates to. I think it's about 10 o'clock, 10:07 our time, okay? And so what's going to be really cool is when Tim Kopra is in space, we're going to link him up with the Finnish students. And maybe we can connect your class at the same time. What we want to do, maybe your class won't be able to ask questions because this is really private telecom that he's having with the Finnish students,
right,
but they'll at least be able to follow along.
Wow.
You know, maybe they will entertain some questions from your students. We also have some high schools in Finland that are participating with the undergraduate. Three universities in Finland have teams, and one team is looking at growing plants in space. The other team is more a computer science team, James, that's looking more at a virtual reality kind of system to basically be able to communicate back down to the ground when there's a problem or an anomaly on the surface of Mars. And so how do you capture that anomaly very effectively using whatever media possible in order to be able to transmit all the right data back to Earth so that the team on Earth can basically assess the situation and make the right recommendation, because you have that 20 to 40 minute lag in time, okay? So this is going to be really cool. As a matter of fact, you should be able to watch the launch from Kazakhstan, read up about it, okay? Learn about Tim Kopra and his crew and what they're going to do, because sometime after the holidays, we're going to be having a telecon with Tim Kopra in space.
That is awesome.
Okay? Yeah.
Wow, what a great opportunity.
You're going to be on TV. I'm obviously transmitting from home, guys, right? And I'm also on vacation.
Oh, wow. Thank you for taking time from your vacation, Charlie.
But this is something that we're gonna be doing in the future, and hopefully next year we will have 10 universities or more in the United States. We'll have 50,000 students in the United States, and we'll be teaming up with students from around the world, and you'll be able to communicate with them virtually. Okay, and Richard, what we could do is we could get your students' permission to see what these other students are doing online, what these Finnish students are doing online, and we'll do that. Remind me after the holidays, we'll invite the students to join. They can look at what these other students are doing.
Great. That'd be fantastic. We're also working on doing a video conference with James Gorman's class.
Excellent,
Yeah.
excellent. And that's exactly what we're going to do, Richard. We're going to hopefully get 50 high school educators, the really good ones like Mr. Luchevsky and Miss Massey, and we're going to connect you all around the country, okay, so that we can be working on lesson plans that other educators around the country could use that connects the students with these problems. So students that are interested in going into the medical field could be looking at the effects of microgravity radiation on astronauts and how do you do that. And you'll have a separate track where you can communicate with other students and subject matter experts at NASA and around the world to help guide you in what you study. Because you know what, I bet you guys learn a lot by just going online, right? Am I right?
Yes.
Yeah.
Right? I mean, there's so much out there that you can pick this up and you can teach yourself, right? And by having great educators like Professor Luchowski, right, they can guide you. But you have the ability to architect your own education and dive in as deeply as you want to learn everything you're going to need. Like James in computer science, tons of courses online that you could go to when in computer science. You can teach yourself Python, right? You don't need a professor to do that, right? But when you have a question, when you want to discuss what you're doing, it's nice to be able to know to be able to go and talk to someone, whether it's in person or online, and ask a question, right?
Yeah.
Or to ask, or to communicate with other students your same age that have done something. And you probably, how many students do video game or gaming, right? How easy is it to communicate with the headset with kids around the world, right? And so we're going to do that. We're going to explore that and hopefully create an environment where you can learn as quickly as possible using what you do best. I mean, you guys are digital natives. You grew up with probably a cell phone in your hand when you were in the crib. And you all know how to use computers, right? And you learn differently, okay? I'm a digital dinosaur, right? They didn't have computers really when I was born, okay? But, and so you learn differently. And so we're going to try to take advantage of that to feed you information so that you can capture it and it's in a format that you understand and you can absorb it as quickly as possible, okay? Any other questions, Richard?
Okay, well, I wanted to let you know Lawson put together a solar oven out of a pizza box and baked cookies. All right. Olivia here worked on a longboard and tested the aerodynamics of different shapes of the longboard. And Ryan and Mohammed built bridges. Did I miss anybody?
Wait. The longboard was a surfing?
No. It's a skateboard.
Skateboard, okay.
And then there's Mary.
And Mary is working on a Rube Goldberg project, and she's learning how hard it is to engineer one motion into another motion.
It's really hard.
As far as learning curves, I think she has the steepest right now.
That's called kinematics, right?
Uh-huh.
That's called kinematics. And there are great software tools to model what you're thinking about when you do that.
Really?
so that you can model those motions, and that's pretty cool. So you can model what you think is going to happen before you actually build it. And wouldn't that be cool? I mean, look at what you have right now. You have Kerbal Space Program, right? Does anybody do Kerbal Space?
Yep.
Isn't that cool?
Yes, it
now,
is.
Now, the orbital dynamics might not be perfect, but it's pretty darn good. And the physics, the way it's being modeled is pretty darn good. So you could do a lot of simulation using these programs so that before you go out and test something, you can actually simulate it first. And then you go out in the laboratory and you test it. And this is not any different than what engineers like myself and researchers, when I was a researcher at NASA Langley, do. And you learn this process, okay? And you go out there, you model something that you have in your mind and how you think it's going to behave. You see something in nature, you try to design something better than what you're looking at in nature and what you observe. You model it analytically using these types of computer simulation models, numerical models that actually simulate the physics of the problem. And then you go out and you build something, and then you go test it. And then you compare what you analyzed to what you tested, and you see if it agrees. If it doesn't agree, then you have to figure out what is missing. What did you do wrong? Was the analysis wrong, or was the experiment wrong? Or did you leave something out of the experimental setup or the analysis? And then once your analysis is very accurate, then you could just use your imagination and design millions of different ways to solve the problem. And you can do it all with the computer before you ever go out and physically build something. Because physically building something and testing takes time, it takes money, and it takes resources. But using the computer and analyzing it first, you can do it many times over to make sure when you finally build it, it's the right design. And also it's safe.
Yeah, it's safer than trying to make a
Yeah.
20 pound.
I talk to them here a lot about failure, and that failure is not an option but a requirement, and they should fail.
Smart, fast, small, cheap, early, and often.
That's what I'm looking for, right?
Yeah.
That's right. That's right. And it's important to fail, and it's also fun to fail. But it's very important you fail in the laboratory and not when a couple of hot pink bodies are sitting on the pointy end of a rocket, right? You want to fail in the laboratory, you want to make all your mistakes, and you want to learn as quickly as possible.
Mel has a question?
Dr. Camarda, for the NASA challenge, are we trying to have like a long-term laboratory on Mars or like a short-term?
What would you want to do?
For
What would you want to do?
For me, a long-term would be good because we're getting more experience with using the Martian landscape, and also if we're going to try and do a short-term research base, and we're going to try and have robots like on the mine materials, it's good to have them constantly there instead of having to bring someone each time back there, or have like a small team that goes there and stays there so that they can maintain everything, but you have regular rotations of astronauts that check up on everything, make sure everything's going well, and you have the support network of other satellites that can boost the transmission speed if that's possible, so that it maybe cuts down from 20 minutes to 10 minutes.
Would you write a letter to the new president of the United States to make sure they understand this?
Yes.
Okay.
Yes, I can.
Because we don't want to just
You will,
go
too.
there and plant a flag and do some nice experiments. I mean, we did a lot of great experiments when we landed Seminary Cruise on the surface of the moon. Okay, we did some real science there, and that was great. And then it stopped. And what we need is for nations around the world to be able to unite and collaborate and make a concerted effort so that we have a sustainable colony on the surface of Mars. and we can grow that colony. And by sustainable, I mean they can support life themselves. They could mine the planet and the atmosphere. They could search for water. They could break up the water into hydrogen and oxygen, oxygen to breathe, water to drink, hydrogen for fuel. You could build methane. You could use methane for rocket fuel. You could mine the planet to build equipment that you need, spare parts that you need, structures that you need. We should be able to do this. I mean, right now we have a space station in orbit since 2000, like 10, 15 years. We've been up in space, continuously manned with a crew of right now 6 people, okay? And we shuttle people back and forth. Wouldn't it be great if we could plant people on the surface of Mars and they live there for over 1 year, 2 years, 3 years, okay? And that's absolutely right. I think we can do it, we need to do it, and what we will learn by doing that, and the technology that we develop in order to be able to do that, can help make this planet a safer, more environmentally sound planet, okay? Because the techniques we're learning to live and conserve and allow humans to survive in space only makes us better in how we understand our own planet, okay? And so it's good for all those reasons. I think you're absolutely right. When we do it this time, we need to do it collectively, basically unite the world in this mission when you think about it. Like I said, 15, 16 countries worked on the International Space Station. I trained in Russia. Back when I was a boy, it was the Cold War. We didn't know whether we were going to be going to war with Russia, okay? And I worked side by side with cosmonauts and trained with cosmonauts, and we fly with cosmonauts in space. So I think it's good for all the sociological, psychological, environmental, and all those benefits, okay? And I think we need to do this not as the United States, but as a united effort with the entire world.
You have another question?
Yes. Another question that I have
Sorry, I
is,
have to go. I have to reply, so
Thanks for
I'll
coming.
let you by the bell.
Bye, Ms.
Nice
Massey.
to meet you.
another question I have is, I've read up on some current ways to get the cost down. There's been certain private space companies that have developed rockets that are able to be reusable in tests. So how will that? So would it be better for NASA to assemble? I think it would be better for NASA to assemble a spaceship in space where it's not as expensive, because whenever I play Kerbal Space Program, at how much weight I do, I have to put so much rocket engines and everything else.
That's right. That's right. And most of the weight, practically 90% of the weight of the rocket is the fuel, right? And it's a tremendous cost. And so being able to build things on the surface of the planet, being able to build it simple. This is going to take a long time for me to talk to you about this, Bill. But there's, this is not a simple answer. And building something to be reusable is not easy, okay? But we have to change the way we think about how we design things. Instead of making them so high-tech, maybe make them, instead of making them ultra-smart and high-tech, making them low-tech, simple, and maybe even dumber, a dumber rocket. But very simple to manufacture using materials that you have in space, whether it's from an asteroid or whether it's from the planet, is probably the way to go. And the way we explore this is by using robots to do that. So there are a couple of commercial companies looking at mining asteroids, and it's Planetary Sciences is one of them that's looking at mining asteroids. We're looking at mining the surface of Mars. And the terminology for that is called in situ resource utilization. In situ means in place. So in situ on Earth would mean taking materials from Earth, and resource utilization is basically taking the resources from the surface of the planet and utilizing them. It's called living off the land. And so if we had a history teacher in the room, or we had, and you're learning about exploration, and you're learning about Lewis and Clark expedition, or if any of you have ever gone camping, what do you take when you go camping? How do you survive if you're out there in the wilderness, right, for food? What can you make? It's better than carrying it with you, right? So when you look at when you read about exploration, okay, whether it's in literature, whether it's in history, whether it's in social studies, when you read about exploration, think about what those explorers took with them. How much did they have to pack? What did they do on their journey? It's not very much different. The technology changed, but the logistics of being able to pull this off is not that much different. We still need food. We still need shelter, right?
Hey, Charlie, I do have a history teacher involved in the project this year. He couldn't make it because he has a class.
Yeah.
One of his pet courses that he loves teaching is the history of science. And he's going to get involved. Matter of fact, I do want to ask you something. I have Jamie over here. We got him out of a sick bed to come here to be our tech person today. He's working on trying to record on a hard drive this video conference, and I'd like your permission to share it with the teachers and people who couldn't be here.
Absolutely, absolutely.
Thank you.
So are you able to record it, Jamie?
I think it is. I haven't been able to look at it, but I believe it's.
All right. If not, the next time we do this, Richard,
Yeah.
we could also do it on video, and I can record it and send you the recording.
Okay. All right.
Okay.
That'd be great too. Yeah.
All
Absolutely.
right. I'm gonna have to take off, guys.
Before you
But I
go,
look forward to. Go ahead.
Before you go, Charlie, going forward, I'm going to put these guys on an assignment to identify their passions in life and to identify some area of this Mars that they want to focus on. So they have like a research question.
Absolutely.
And then we'll do, their final paper is due in March, which gives us time for them to present the ideas to you, and then we can, hopefully we could, if we can, organize a field trip to Langley to watch the university people present. That would be awesome.
Absolutely. And Richard, when they're doing this exercise, I want the students to think about how what their passion is, how that could be applied. And so in order for them to do that, they need to read up about space, about traveling in space, what it takes, understand what it takes to go to Mars in some aspect of it, and then be able to make that connection between your passion and why it's important, why that passion is important for us to be able to go to space successfully, go to Mars, live in Mars successfully, grow a colony on Mars, and what will it take to do that? And then to be able to sell that to a team of people at NASA, why this is important, why this is critical.
So,
Okay?
Can I ask a quick question before you go?
Yeah.
Do you happen to know at what speed you begin to enter relativistic time? Like, for speed of light, as you get towards the speed of light, time for the object moving slows?
And when it becomes negligible, right?
Yeah.
When you can't neglect it anymore, and that I don't know. Okay, it was a long time since I took physics. Where's your physics teacher? Where's your physics teacher in the school?
Yes, we have a couple of them. I've invited them here, but they couldn't make it. So we'll track them down and get that question.
Of your physics teacher. Okay. Matter of fact, we could probably Google it, right? You could probably take your phone right now and Google that. You see, I didn't have Google when I was a kid, but really, what you want to do is you want to go to your physics teacher, because what you're asking is, when does it become so important that you can't neglect it? And that depends on when you need to make that calculation and how you're going to use that calculation. For instance, if you're using it for orbital mechanics and you're going very far away, you know, if you're just going to the moon and it's close, it might not make that much of a difference. When you're going light years away, okay, like some of the probes that have left the galaxy, then it could become important. That question doesn't have one answer, right? It depends on when that error in your calculations becomes important, and you can't neglect it any further, right? Otherwise, you're going to miss the entire planet. Okay?
Right. Yeah, I was just asking because I was doing some work on a rocket to Mars idea earlier in the year, and I found out that going the speed of light from Earth to Mars would take, for the rocket itself, would take, or the people inside of it would feel like it took 13.5 seconds. So.
I don't know if that's true. Oh, it would feel like it took 13.5 seconds.
Right, and it would affect their body that way.
It would really take 20 to 40 minutes, but it would feel like 13 seconds. Okay.
One of Hunter's passions is near, or hope he wants to do greater than light speed travel. So I got a feeling I know where he's going to focus his interest.
All right, you're going to be a physicist, Hunter. You got to be a physicist to do this. All right, guys. Good luck. Have a great holiday.
Thanks.
Thank you.
I'll see you after the holidays.
Thank you.
Thank you.
Well, so we have ourselves, we all.
Okay, stay around. Let's talk about this. Let's kick this around a little bit. I'm still taping this. Okay.
Take each other around.